Hi everyone, and welcome to this first video on a series that is based on Lazarsfeld's pair of books, Positivity and Algebraic Geometry. I'll go section by section, starting with 1.1 preliminaries on divisors, line bundles, and linear series, and each video will be focused on a subsection of these sections. And so I'll proceed with 1.1.A for this first video, which is a review of divisors and line bundles. So throughout, I'll let X be an irreducible complex algebraic variety, and I'll let this curly kx be the sheaf of rational functions, on X. I'll let kx star be non-zero rational functions, or the sheaf thereof, and I'll let Ox be the regular functions, and Ox star to be nowhere zero regular functions. Okay, so let's first define what it means to be a Cartier divisor. So, definition, a Cartier divisor on X is a global section D of this quotient sheaf of non-zero rational functions by the nowhere zero regular functions. So these form a group which I'll denote by div x. And so concretely, right, D is represented by the data UIFI, where UI is an open cover, on X, and Fi is a local section of the sheaf of non-zero rational functions over each UI, such that on overlaps, Uij, which is my notation for the intersection of two open sets UI and Uj, we have Fi is equal to Gij Fj for some Gij nowhere zero rational or regular function, sorry. Uij Ox star. Okay? So that is to say, it's a globally compatible system of local rational functions or rational equations. Okay, so two collections UI FI and VJ HJ define the same data, that is to say the same Cartier divisor, if after passing to a common refinement, local equations differ by units. So multiplying a local equation by a unit does not change the divisor. And this is because a unit has no zeros and it has no poles. So these are invertible. And their inverses are regular functions as well. Okay, now I should have defined this a bit earlier, but the group structure is as follows. Suppose I take D to be defined by the local data, UI, FI, and E to be defined by the local data, UI, HI, then I can assume they have the same open cover because I can just pass to a mutual refinement. D plus E is defined to be the data where I take as the open cover that is in each of these two, and the local rational equations are given by Fi times Hi. So I just multiply the local rational equations, cutting out these pieces. And the support of D is defined to be those points in X such that a local equation for D is not a unit at the point X. Okay. Another notion is that a divisor is effective if it can be represented by regular local equations rather than just rational local equations. And so we'll write D greater than or equal to 0 for this. And so it has zeros, potentially, maybe not, but no poles, as we can see by the description here, right? If we were to have poles, then the inverses, or rather, if we were to have poles, then this would not be a regular function, it would be a rational function. So let's give some examples. First example, let X be spec A. So I'm taking an affine scheme. Suppose it's integral. and I'll take some non-zero function f on spec A. Then this determines an effective Cartier divisor, which I'll sometimes just abbreviate as divisor, given by its vanishing locus, provided f is a non-zero divisor. And why is that? Well, on X, it is represented by the pair XF, right? So on an affine integral variety, one non-zero regular function cuts out a Cartier divisor. Okay, now I can take another example, this time projective. So I'll take X to be n-dimensional projective space with coordinates x0 through xn, homogeneous, and I'll take h to be the vanishing of the first homogeneous coordinate. Right, so the hyperplane x naught equals 0. And so on the distinguished open set ui, given by the non-vanishing of the homogeneous coordinate xi, we can define these functions given by ratios of homogeneous coordinates, so that on overlaps, we have, just to make sure, fi equals x naught over xi, which equals xj over xi times xi, or sorry, x naught over xj, and this equals xj over xi times fj. But we have that xj over xi is actually nowhere 0 as a regular function on these overlaps. So h equals a of x naught is an effective Cartier divisor. Okay. Let's give one more example. So I'm going to let C be a smooth curve. Then every point has a local parameter Tp. So the divisor P is locally defined by Tp equals 0. So formal finite sums, and this is foreshadowing of what will come next, gives rise to a Cartier divisor. These formal finite sums of divisors, or finitely supported sums of divisors, will be called V divisors. Or, formal finitely supported sums of codimension 1 varieties, irreducible, are going to be called V divisors. And these are going to be somehow dual to Cartier divisors and equivalent to them in many cases. So on a smooth curve, at least, Cartier divisors and formal sums of points actually coincide. Okay, great. So this is an important time to now give a definition. So let X be variety, right? Under all the conditions that I started with. V divisor is a sum over codimension 1 prime, which I'll say irreducible, and I'll assume this is normal, and regular in codimension 1, so that things behave nicely. Then this is a formal sum of the form AW times W, where AW are some coefficients. And there is finite support on the entries. Okay. So, great. So yeah, it's a finite sum, and I'll define a K-cycle just to generalize this. A K-cycle is a finite sum AI VI, where the coefficients are integers and where VI and X are irreducible k-dimensional subvarieties. So under this definition, V divisors are just one cycles. So the group of K-cycles under addition is denoted by zk of x, and I'll note that, oh sorry, this should be n-1 cycle. I always mix up whether it's codimension or dimension, but in this case it's dimension, so this is an n-1. I'm used to intersection theory where you often grade by codimension because codimensions add. So the group of K-cycles is denoted by zk of x, and we denote in particular the group of V divisors to be W div, which is of course Zn-1 of x. So these are formal sums over codimension 1 subvarieties. Okay, so as we saw on a curve, these were just, so example, on a smooth curve, the V divisors are equal to the direct sum over the points in C, of ZP. So because points are codimension 1, then on surfaces, these are going to be formal sums of curves. On threefolds, they're formal sums of surfaces, and so on and so forth. So okay, I'll define the cycle map now, which compares Cartier and Bay divisors. So we have a natural map from Cartier divisors to Bay divisors that sends D to its class as follows, where this is defined to be the sum over V of the order of vanishing times V, and this is over codimension 1 irreducible subvarieties of X, which I'll suppress. So the way that we can define this order of vanishing is as follows. So if D is defined by the data UI Fi, and V intersects UI non-trivially, so this is for every UI that intersects V non-trivially, then define the order of D along V to be the order of vanishing of these Fi along V. And these are well defined because these functions agree up to units. So the orders of vanishing are well defined because the order of vanishing of a unit is just 0. So proposition, the cycle map is injective for normal varieties. So let's give the proof of this. So first, suppose D maps to 0, then that is to say that ord VFI equals 0 for all codimension 1 irreducible subvarieties V in UI. So Fi has no 0 or pole along any V. And so because X is normal, can check regularity in codimension 1. We have that OX of U is equal to intersection equals 1 OX V inside the rational function field. And since ord V Fi is necessarily non-negative for all V, it follows that ord V Fi inverse is also greater than or equal to 0 for all v, which shows that fi is, fi inverse is a regular function on ui. And so this implies that because the inverse is a regular function, fi is a nowhere zero regular function on ui. So every local equation of d is a unit, which implies that d equals 0. Every fi is a unit. Great, so this shows that the cycle map is injective. And we have something more, which is that if x is non-singular, the cycle map gives an isomorphism from Cartier divisors to Weil divisors. So I'll go through the proof, and we only need to show surjectivity. So non-singular implies normal. So we only need to show surjectivity. So I'll let v and x be an irreducible codimension 1 subvariety. So I want to show that v is Cartier, and it suffices to do this for just a single codimension 1 variety, as we'll see, because any Weil divisor is integer linear combination, and we can just locally cut it out, by appropriate equations. So we want to show that v is Cartier. So take any x and v. By smoothness, the local ring at x is regular. Right, we have a regular local ring. So it is a unique factorization domain. Now, the ideal of v at x is a height 1 prime in the local ring but in a UFD, every height 1 prime is actually principal. This is a really fun ring theory exercise if you've not done it. So we can write P as being generated by a single element F, where F is in the local ring at X. So V is locally cut out by one equation, hence it is Cartier. And and the result follows. Okay, so I'll call it from here, and in the next video I'll talk about principal divisors, linear equivalence, the class group, the relationship between divisors and line bundles, when line bundles can be represented by divisors, the Picard group of line bundles, let's see, and the canonical bundle and the canonical divisor. So I think I'll stop at around halfway through 1.1.A and maybe just split these up into subsections in Lazarsfald's book so I can keep this as bite-sized as possible. Thank you for watching this video, and I'll see you in the next one.